Good morning, and thanks for having me for this presentation. And apologies again for not being able to join the General Assembly in person, but I had some personal issues that prevented me to travel. Um, so the talk will provide essentially a short, let's say, historical overview of how AI has been used for cybersecurity in certain applications, and how actually an active adversary can break into these systems by attacking the machine learning component. Before I start, just a few words about the lab I'm part of. It's called the Safer Lab, and it's a joint lab between the universities of Cagliari and Genova in Italy. And we are more or less 50 in Cagliari, and the rest is staying in the north of Italy in Genova. And we cover different areas of research, AI security, biometrics, cybersecurity, for instance. And I'm in charge of the AI security part, where we do attack and defense against machine learning models and secure AI for cybersecurity, and also a bit of LLM and agentic security more recently. So, from my experience, I can say that the problem started around 2004 when we had the first anti-spam filters and anti-malware detection models that basically were being attacked actively by adversaries. And of course, the initial models were simple, yet effective. Like in most of the cases for anti-spam filters, you had linear models, and these were used to separate, legitimate and spam emails. So in this case, if you look at the content of the email, which is, this text is what the model is processing, essentially it's very clear if you know the weights of the model and how the model is trained. Basically, it's easy to understand how to fool it. So in this case, if you have a spam email that contains some of the bad words known to the filter, what you can actually do is essentially to modify these words and also add some good words to downgrade the score of the model, and then have your email classified as legitimate. Here, the intuition is that the attacker could modify words that have a high impact on the model decision, and then basically decrease the score. Where here, of course, the positive score means malicious, means spam. So that was fairly simple to show. And what was not clear at that time was that essentially, if you have more complex models, um, these also could be trivially bypassed. And this was not clear up to the point where, in certain papers, this is just an example, people have been claiming that this sort of complexity of the models basically hides some of the details that the attacker could exploit to essentially bypass the model, making the system more robust in a sense. So this is basically a claim of security by obscurity. And as many of you know, complexity is instead typically the enemy of security, right? So if you have a very complex system, it's more likely to be easy to find vulnerabilities in that. So the idea that we had at that time to show that this claim was wrong was basically and this is the main intuition behind all of the attacks that you see nowadays, that these attacks on machine learning models or AI can basically be staged as optimization problems against such models. So that was the main idea that was driving this follow-up work. And the idea is that, again, if you consider a model that outputs a positive score for malicious instances, what you would like to do is to manipulate this instance to have a negative score, so to reduce the score as much as possible. So this is clearly a minimization problem. And all of this area of adversarial machine learning clearly makes sense only because the attacker is constrained. Because if you had no constraint, then the attacker would always win. So the overall point of studying this area is if the attacker is constrained, and he has to be able to attack the system by by changing the samples within these constraints that are fixed. So in the case of emails, you can say you can bound the number of words that can be changed, for instance, or in the case of malware, you can modify samples, but they have to preserve functionality. So within these operational constraints, basically you have to find an instance that bypasses model detection. So what you have here is basically this minimization problem with constraints, and then in most of the cases, this is just a nonlinear constraint optimization problem that you can solve by gradient descent. So that's basically the short story about all of this area of evasion attacks against machine learning models. Of course, at that times, we tested that against subvector machines and neural networks, simple neural networks on images, and it was nice to see that to fool a model that discriminates trees, digit 3 versus digit 7, what you just need to do is to remove some of the pixels. Okay, so in this case, the constraint was to change the image by modifying only a few pixels. And this was already kind of an evidence that to evade a model, you really don't need to mimic the target class. So we don't need to change the tree, the original tree, to look like a 7, but just it's enough to just change it a little bit to be different enough from the other training instances of 3. And this is a concept which holds in all of these applications of AI, where when you train the model, you tend to believe that it should really learn the semantics or the meaning of certain objects or classes, but instead, in most of the cases, it's just using certain spurious correlations to separate them. And this is exactly what makes all of these models extremely vulnerable to this type of attacks. Then, of course, we also tested the same attack on the PDF malware detection system that I described before, where the authors made the claim that nonlinear models should be more robust. And what turns out is that basically the evasion rate still grows a lot, also in the nonlinear case, when you increase the number of injected objects that you have in these PDF files. So to make a long story short, the answer is that all of the models are, even if they are very accurate, they are very fragile to this type of well-crafted manipulations that target the models specifically. This was prior to the discovery of adversarial examples that happened, as you probably know, in 2014 by Christian Szegedy, Goodfellow, and the rest of the team from Google Brain at that time, where they basically were studying interpretability of deep models to understand why they were so accurate and what type of features they learned from data. And they incidentally discovered that when you slightly perturb an input image, you can basically fool a model very easily. So if you look at this perturbation, of course, it's not random, but it's just slightly modifying the input image to have it misclassified as something different with high confidence from all of these state-of-the-art models. And of course, this was extremely surprising to discover because these models were extremely accurate, claimed to have superhuman performance, and yet they're super easy to fool. And again, the underlying algorithm to find this perturbation was still computed by doing optimization over the scores of the model. So it's basically by gradient descent. So it's basically the same strategy we were using 1 year before. And since then, these attacks have become pervasive, and we had countless examples in different applications. Here you see some of the most famous ones. So you can build these eyeglass frames to impersonate other users, or you can apply this camouflage to traffic signs to have them misclassified as a different sign. You can slightly perturb input audio to have the transcription to text completely changed, like in the 2 sentences that you see here. And the same kind of optimization can also lead you to attack large language models and bypass basically the guardrails that can be put in place, or the alignment mechanisms. So that's basically the scenario. But of course, this was all done for the simple case, let's say, of additive perturbations on image models. So when one considers more, or even in the PDF case, it was just a toy example where we can basically treat the PDF classification as a text problem and just add objects inside the PDF. So it was not really challenging in terms of designing the perturbation for this type of data. But if you consider different tasks and maybe also more realistic malware detection problems, well, it becomes a little bit more complicated to understand how to optimize this type of noise on different type of data, especially because um, in most of the cases, we cannot just do, this additive perturbation delta. So we cannot do the original image X plus some perturbation. But in the case of malware, for example, adding bytes to the original program in the sense of the plus operation doesn't make much sense. So you need to find other types of transformations and optimize over these different transformations. So in 2017, what happened was that these type of deep architectures were started being used for malware classification as well, in particular for classification of executable programs as malware or goodware by just looking at the bytes of the compiled program. So in this case, what was done was to consider the input sequence of bytes to the machine learning model. These bytes are treated basically as tokens in language models, so as words. You can map them onto an embedding space, and then on top of that, you can basically train your preferred neural network architecture. And in this case, it was a kind of convolutional network. So this was really a first attempt to throw deep learning into the problem of malware classification and see basically what happens. And what the authors reported was really amazing performance in this case. So they had like very high accuracies on certain data sets that were built. They were advertising this on Twitter when it still was a useful social media. And I reached out to them by saying, but it's a very interesting work, but basically, are you aware of this problem of adversarial examples? Meaning that if I slightly perturb the input bytes, I might be able to fool the model very easily. And the authors were replying, oh, it's too early. And basically, the argument was also that modifying malware is not as easy as modifying images because, you cannot just change the bytes as you do with pixels without corrupting the malware functionality. And then basically we show that instead you can do it in an easy way, and you can fool this architecture that is called malconf, as well as many similar models. So how we did it? In the very first instance, we just added padding bytes at the end of the file. And you can do that by basically without compromising the functionality at all. And it's also not so trivial to strip those bytes by easy detection mechanisms. So there's no trivial way to prevent this, but yet you can add padding bytes at the end, and this can be surprisingly effective in bypassing detection, especially, of course, when you optimize this by looking at the gradients of the network. So again, gradient-based attacks here were surprisingly functional and effective against this model. Then we studied many other transformations that you can apply to executable files without corrupting functionality. And in particular, we show that you cannot just pad bytes at the end, but basically you can abuse the file format in many different ways. So all the colored areas that you see here, those are bytes that can be either added to the initial program or changed in the initial program without compromising functionality. So you have all of this space, let's say in the executable, that you can basically inject or modify whatever you want. And this led us to develop much more effective attacks that can fool malconf and other similar deep learning architectures for this kind of problem rather easily. In both the white box case, so where you look at the gradients of the model and you have access to the model, but also in the black box case, where you don't know the model exactly, but you can query maybe a service that is based on the model and exploit feedback. And in this case, what you can also do to reduce the number of queries is instead of optimizing the bytes one by one, you can basically take chunks of bytes from benign programs and decide how to combine them. So with this kind of reparameterization, you can really decrease the number of queries that are required to full detection. And we proved that empirically that basically you can bypass state-of-the-art detectors as well as malconf. Okay, so not only neural network-based models, but also models that are based on decision trees and so on. Surprisingly, when also tested against VirusTotal, so against real anti-malware scanners that are hosted on this service, we discovered that some of the attacks that we optimized against the academic detectors, let's say, were also quite successful against these anti-malware services that were only doing static analysis on VirusTotal. And this was quite interesting because we never optimized the attack against the specific VirusTotal services, but just against the detectors, the academic detectors. And you see that some of the antiviruses hosted on VirusTotal were really sensitive to this problem. They were able to spot more than 90% malware without any change, but then they fall down to 30% detection after we manipulate some of the bytes. And we just adding content here. We are not obfuscating anything. So the malicious content is still there, probably in the clear to be detected, but it's basically not seen anymore by the detector. And this is, if you want, also proof that these antiviruses are really using machine learning models to do the detection because they turn out to be very sensitive to the attack. So this was a kind of side result that was pretty interesting to us. We've been doing a similar thing for Android malware detection, where we studied the robustness of these detectors again against injection of content. And even in the case of this popular Drebin detector, you can show that if you inject a number of components into your Android application, you can basically drive the detection rate of this anti-malware solution to zero by just adding fewer components in the APK file. The nice result here that one can obtain is on the defense side. So from the side of the defense, the good news is that you can find a very effective defensive mechanism in this case. There are some, let's say, theoretical derivations that you can do, but basically you can connect the regularization term of your machine learning model to the type of noise that you craft on your data sample. And in this case, it turns out that if one uses this L infinity penalty for regularizing the machine learning model, what happens is that you get much higher robustness than you have in the standard case. So the green curve here is the vanilla detector that was proposed, the original one. And you see that it can be fooled very easily. The blue line is basically a combination of multiple classifiers trained with the same rationale by perturbing the training data and then averaged. And when you see that averaging multiple classifiers gives you some more robustness because the performance, the accuracy, the detection rate degrades more gracefully, but it's not very much more than what you have in the initial stage. The red curves are instead the models that we regularize with this optimal regularization term, and you see that they are much more robust, meaning that you need to modify many more components than you need in the original case to bypass detection. And there's no magic behind this. The practical reason is that when you use this type of regularization, you're basically equalizing the feature contribution to the model. So now there are not anymore features that have a lot of weight, that have a lot of importance for the model, but the decision that the model makes is using more uniformly the contribution of all the features. So at the end of the day, the attacker is constrained to manipulate more features if they want to have the same decrease in the output score. So that's why basically this improves robustness by a large margin. Very recently, all of the attack that I described was just simulated. So we never modified the real APK, but just simulated the impact of the attack by changing the features that are provided to the model. And only very recently we worked on an attack that is really modifying the APK files. And essentially, we show empirically that you can uh, really inject this and obfuscate some of the components in the APK file in the application without really having any side effect. So people have been showing that attacks on these malware classifiers are possible, but at the cost of injecting large portions of benign programs, for instance. And in this case, instead, we show that you can do this with very fine-grained manipulations, and this increases the success rate of the attack by a large margin, and also the decreases a lot chances that you break the application functionality. So in this case, we are really close to the ideal case where you just manipulate the feature values, as we showed in the previous work. As another example, we've been working also on improving web application firewalls against SQL injection attacks. So what we noted in this kind of recent development was that some of the open source filters like mod security using the core rule set consist of basic rules developed by domain experts that would stop attacks. And they are just considering for each rule a severity score, which is how much the attack could have an impact, or how strong the attack could be, or can be damaging the system. So that's basically what this severity level means. But then what they do in practice is that they set a threshold, and if the severity of the rules that are triggered by the input query exceeds this threshold, they say that the input is likely to be an attack, and then deny access to the server. So essentially, what these people have been doing, probably without even noticing that, is that they were using a linear classification model where the weights that they associate to every rule was basically manually determined. Okay, so the first thing we did was to, instead of manually assigning the weights to the rules, we just optimize these weights by using a machine learning model trained on the traffic that you may have collected from some web service. And this already improves the performance by a lot. So we went from 60% to more than 95% detection rate when the false positive rate is very low, meaning 0.1 or 0.01%. Then the second thing we showed in this paper is that by applying the same idea we used for Android, so having weights that are more uniform rather than assigning a lot of weights only to few rules, it turns out that you can increase robustness also by a large margin, in this case, against adversarial SQL injection attacks. So these are attacks where you take the input SQL query and you basically modify the query by trying to maintain functionality while being deceptive for the model. So this is one of the few cases, I think, where the idea of having an accurate and robust system really works. Conversely, in contrary to the case of images or computer vision, where it's really challenging to find this sweet spot. So in these cases, in cybersecurity, I think we have more hope because we can essentially, the attacker is more constrained. It has less degrees of freedom to manipulate data. And this is, let's say, what you can exploit defensive side to improve the robustness of the overall system. I have just a few slides to conclude to discuss a little bit attacks on language models, but I think we will cover a lot more in the remaining talks in this workshop. So the idea of this attack again, these attacks again is that of forcing the model to output an affirmative response, something like you want to bypass this guardrail that is not giving you the instruction to build a bomb. So what you do is you force the model to respond, sure, here are the instructions on how to do that, and you optimize this response by changing by appending some of the tokens to the input prompt. So you force the model to unlock a response, and you see that these apparent nonsensical tokens are those that instead bypass the alignment of the model that enable you to do that. Now, what's the drawback of this? It's that this text has a very, it's not very likely to be generated by the model, so it has um, essentially low probability of being generated, and you can exploit these to detect the presence of these portions of weird text or instructions that aim to unlock the response. So to prevent this kind of detection, we worked on an approach that instead of appending these weird tokens at the end, tries to replace every word with a synonym while keeping, the intent of the initial prompt of the initial request. So here you have just an example that you replace give with provided and instructions with guidance, and this is enough to unlock response from the target model. And what we also do is to, instead of optimizing an affirmative response, we try to shift the malicious request into a region of the latent space where you know that the model responds instead of refusing. So this was increasing the success rate of the attack also by a large margin. And what you see here is just how easy it is to detect some of the other attacks. So the red and green curves here are attacks that have high perplexity, so they can basically be easy to be detected. Whereas latent break, which is our approach, only slightly improves, slightly worsens the perplexity with respect to the initial prompt. So it becomes much less detectable than the others. I'm gonna finish with this last slide. I like very much this paper from Rando, Zhang, Carlini, and Tramer, where they compare the transition that we have experienced from adversarial machine learning, from the traditional approaches towards this new LLM era, let's say. And they noticed that they highlight that we were essentially attacking toy problems before, or these computer vision attacks, using a clear mathematical formalization, so optimizing over these LP norm constraints. But even if the problem has a clear mathematical form, it turned out to be very complex to be solved. So still, we don't have any effective defense for the computer vision case. While I hope I have convinced you that something can be done more effectively in the cybersecurity space because the attacker is more constrained. And now, what happened when we moved to LLM agentic AI is that now we have more realistic attacks. We have less, let's say, mathematical support. But now the thing is becoming very interesting because these attacks essentially can really target existing systems and give rise to this new type of vulnerabilities that are discovered day after day. And the problem that I see here is that given that we have no mathematical support as we had before, the concept of security here is ill-defined. So we don't have a clear definition of even what aligning these models mean. And so even evaluating them is becoming really, really challenging. So I would love to see if any other solutions emerge in the remainder of the workshop. And with that, I want to thank you very much for your attention.